Hi guys, good morning. Welcome back to new video. Ki hal chal? I hope you guys are doing good. In this, we're gonna see problem. Check if digit are equal in string after operation 1 and operation 2. Again, both are same problem, just the constraints are different. Just a disclaimer, the video gonna be a bit long as you can see. I'll teach you a lot of great concepts. And again, no worries if you were not able to solve it. There is nothing new which you should be knowing to solve this problem. Again, nothing new. If you would have solved practice problem sheet, just medium questions itself, again only medium question practice problem sheet for math, if you have solved medium question itself, you will be good to solve this problem in the contest. Let's start off. Now again, before starting, please make sure that like target is 75, no, 100 likes, because it took a lot of effort. In this, we are given a string s consisting of digits, and we have to perform operations repeatedly until the string has exactly 2 digits. What is the operation? Operation is nothing but choosing consecutive digits, which means the first and the next digit, and then summing that and doing a modulo by 10. Obviously, I have to replace s with the new consecutive addition, ultimately return true if the last 2 digits which are remaining are same, otherwise false. For example, let's take this case. I will take two consecutive one, add them, do a modulo by 10, I'll get a 2. Same way, I take two consecutive, add them, do a modulo by 10, I get a 9. Same way, I'll take two consecutive one, add them, modulo by 10, I get a 2. So this is one stage done. As you can see, after one stage, I have one less digit, right? Okay. Next stage, again, I will have to keep on doing until in the last stage, I will have only two digits. I have to keep on doing that. And obviously, I will have digits itself because I'm doing a modulo by 10, which means anything doing a modulo by 10 will have value less than equal to 9. Okay, 2 plus 9 mod by 10 got a value of 1. 9 plus 2 mod by 10 got a value of 1. Now, in this stage, again, I have one reduced value. You will see that now I have both digits are equal. Answer is true. If I just show you another case, obviously in this 3 plus 4 mod 10, 7, 4 plus 7 mod 10, 1, this plus this mod 10, 5, 8 plus 9 mod 10, 7. Again, you will see earlier I had 5 digits, now I have 4 digits. Okay, again do the same thing. 7 plus 1 mod 10, 8, 1 plus 5 mod 10, 6, 5 plus 7 mod 10, 2. Now I have one less digits, one less number of digits. Again, 8 plus 6 mod 10, 4, 6 plus 2 mod 10, 8. Now I have only 2. I have to stop right here. I saw that in the last, both are not same. Obviously, my answer is false. So in the first approach, in the first variation, the constraint of n is 100. And you can see at every step, I am reducing one less digit. It will go, this entire process will go roughly for n number of steps, or you can say n minus 2 number of steps. At each iteration, I am going on to all the n digits, right? So n digits stepwise, I can have roughly n steps. Again, you can also say exactly n minus 2 steps, because if I have 1 2 3 4, sorry, it would be n minus 1 steps. Obviously, you can just discard the last one, so it will be n minus 2 steps, but roughly it will be n steps, and each step taking n iteration. Time complexity will be O of n square, and that is the reason O of n square for this constraint will work. So n of 100 will work, and thus n square will work. How I will do it? Same thing. Until my size is more than 2, just repeat the process, which means that this main while loop will run up till O of n time. And the inner while loop will just go on to all the digits, get the 2 digits, or I should say 2 consecutive digits, add them, do a modulo by 10, and get a new digit out, and put that in the new string. So for one string, I'm making the next string by taking the modulo, and ultimately checking in the last step that if both the characters are same. If yes, I'm great. If not, I'm not. Time will be O of n square and space will be O of n, because you are using a new string which will take extra space. Now, how to optimize this? Obviously, we'll have to optimize this, because in the next step, in the next follow-up, which is a hard problem, you are given the n as 1e5. In that case, let's figure out again, every time you have to do anything in CP, in maths, in programming, make sure to observe things. Observation is the key to anything. Now, ultimately, we realized that ultimately I will have to get two states. One is this, one is this. And I have to make them or ask them if they're equal or not. Now, let's see how I will make it. Obviously, I cannot go these stepwise thing. I cannot do that. In that case, let's see how I will achieve this number without going in this stepwise manner. Again, I'm only taking one of them. I discarded, as you can see, I discarded the right one because I'm only focusing on a small problem and trying to figure out a pattern from this. Now, I saw that okay, 3 plus 4 mod 10 was happening. Okay, again, I'm not, so ignore this, ignore this, ignore this. Only focus on 4 plus 7 mod 10. Okay, 7 plus 8 mod 10. Okay, next time this plus this mod 10 is happening. So a plus b mod 10, right? And then there is b plus c mod 10. I am adding that. So I can easily write it as a plus 2b plus c mod 10, right? The same thing I did. So here I wrote it as 3 plus 4 plus 7 mod 10, right? Which ultimately can also be written as 3 plus 2 into 4 plus 7 mod 10. Same way for this thing, I wrote it as 4 plus 7 plus 1 more 7 plus 8 mod 10. How I can write it as 4 plus 2 into 7 plus 8 mod 10. Again, ignore this thing. Now you have expanded. I have expanded piece of expressions. Now I am using those expanded piece of expressions. Okay, now let's proceed forward downwards using the same thing. 3 plus 2 into 4, 3 plus 2 into 4 plus 7 plus 4 plus 2 into 7 plus 8. Again, doing a mod 10. How I will just club it up? 3 will be there, then 2 into 4 plus 4 will be 3 into 4, a 7 plus 2 into 7 will be a 3 into 7, and then a 8 mod 10. Now can you see one very interesting pattern which you have already seen before many times? 1 2 1 1 2 1 1 3 3 1. Did you see a pattern? 1 3 3 1 1 2 1 1 2 1. Did you see something? Yes, you must have seen this is nothing but a Pascal's triangle. So a Pascal's triangle, again, this looks like this. It simply says that you have 1, 1, 1. Any time you want to get a number, you can get it from two of its parents. This is a Pascal triangle. Again, if you don't know what a Pascal's triangle is, we have already discussed the problem on Pascal's triangle, which is a very easy problem. Make sure that you know about the Pascal's triangle. Again, link in description. Again, if you would have done the practice problem sheet, you would have already known about the Pascal's triangle. Now, coming on back, I realized that okay, this is nothing but the Pascal's triangle pattern, which I can infer from this. Okay, anything else which is happening? Obviously, yes. There are some coefficients, which is 3, 4, 7, and 8. Pascal's triangle has one thing, which is 1, 3, 3, 1. Okay, this is there, but there are some coefficients as well, which means these things. Or I can say some constant as well, which are these things: 3, 4, 7, and 8. And these are nothing but the input: 3, 4, 7, and 8. Okay, now I realized I know something of the sort that okay, I can use Pascal's triangle. Now, if you don't know about the property of Pascal's triangle, again, usually Pascal triangle is something like a triangle, right? But for mathematical terms and understanding much more easily, we always try to represent this as like this, right? A triangle form like this. Because again, a triangle form like this, it is much more easier to work on indexes when it is on a square or a rectangle pattern. So I will represent the Pascal triangle as a form of a triangle, but obviously as a square and then a rectangle like this. What this will help? This will help just you to know, again, although you must have known already if you would have solved the practice problem sheet. If not, then even if you have solved the DSM master sheet, still in that there's a problem which covers Pascal's triangle. But any which ways, you will see that a Pascal, if I just write it down and if I write the indexes, this is a simple Pascal's triangle, exactly same as what we have shown here. But just to indicate that at a row 4, at a column 2, the value is 6. How to know that part? Nothing. 4C2. 4C2 is 6. And that's how I can easily, at any point in time, for any row and any column, I can figure out what value will be there inside my Pascal's triangle. Now, why is this useful? We will see it later on, but this is what you should know for sure about a Pascal's triangle, right? Again, Pascal's triangle, I'm hoping that you must be knowing what Pascal's triangle is and how to compute its values. But in the practice problem sheet itself, we have seen that how we can optimize and work on the Pascal's triangle. Now, coming on back, we now know that at any row and column, I can easily figure out any value of the Pascal's triangle. So, if I ask you one very basic thing, if I ask you at the third row, what all values will be there at the third row? Again, make sure indexing rows are starting from 0, 1, 2, 3. And the third row, if I'm asking what all values should be there, you will simply say it will be 3C0, right? 3C1, right? 3C1, 3C2, and 3C3, and 3C3. So my Pascal's triangle, again, you can imagine it as binomial exponential, binomial coefficient as well, or there's a simple term 1 plus x h power p. Again, there are multiple ways to go about it, but the simplest is Pascal's triangle. That you can easily see that I can find for any row, I can find the actual actual coefficients just by its row, and obviously I can go stepwise to all of its column. How this will help me? This will help me because if you remembered, we remembered that my n was 5 and I was taking starting 4 values. For starting 4 values, I know if I have to take 4 values, I have to take a row of 3. So I can easily say that for n minus 2. So the coefficient will be n minus 2 C0. So it is n minus 2 C0, n minus 2 C1, n minus 2 C2 up till n minus 2 C n minus 2. So this is n minus 2 C0, n minus 2 C1, n minus 2 C2 up till probably n minus 2 C n minus 2. This is how I can easily derive the coefficients. And the actual constants are nothing but the input value of the string. The input value of the string. And again, making sure that I have to do a mod by 10. So now, whatever I was doing earlier in this tree formation, stepwise, I have achieved a formula, and that formula is nothing but taking the actual constants and the coefficients for them can be determined with the help of the Pascal's triangle formula. Now, the catch here is, if you have got this formula, right, how will you solve this? Aryan, isn't it easy? I know that I have watched the videos for nCr, so I know how to compute nCr. I have to just do a mod by 10 and then I will get the value. Obviously, I have already seen and I have done the practice problem sheet, and I know that in the basic modular arithmetic problems, how we do the, if you have done basic modular arithmetic problems, you must have seen that we already have, a plus b mod 10, and it will be a mod 10 plus b mod 10. If I have a into b mod 10, then it is a mod 10 into b mod 10 entire mod 10. So you know the basic modulo. Again, if you have not done it, make sure that you practice from the practice problem sheet. Now coming on back, we realize that this is simple, but the entire expression is, how will I get the value of this? How will I get the value of this? For that, let's see how we can do it. But again, for that, at least I'm expecting that you know nCr, what nCr is. If you don't know what nCr is, link will be in description. You can just simply go and search for maximum and minimum sums of at most k subsequences. If not, then come here and search for maximum and minimum sums of at most k subsequences in the medium category for math and number theory. You will find the problem. Just make sure that you go and watch this specific problem for nCr. If you don't know about nCr is. Now, imagining now you know about nCr, you will see that I have discussed that to find nCr, what we do? We say nCr is n factorial upon r factorial into n minus r factorial. And again, considering I have to do a mod with p, because obviously factorial values are very high, I have to do a mod with p until unless else it will not fit in the integer or the long itself. So I just, because this is the value and I have to do with mod p, I do an inverse modulo of them. And for the inverse modulo factorial, I will have to make sure that the p is a prime, because for inverse modulo, p needs to be prime. Again, if you don't know about inverse modulo, all that stuff, make sure that you check out this video. Coming on back. Again, even if not, then there's one more problem which will cover inverse modulo and all that in very deep, which is this one, 3405. Again, link in description. Coming on backwards, we realize that I can simply apply nCr, but the nCr can be applied when the modulo is done with a prime number and not with any other any other numbers. So let's see. Now my task becomes, I have to do a x mod 10. Again, I'm just replacing nCr with x. And now my target becomes, find x mod 10. Or I should say rather, x mod a non-prime number. So how to achieve that? Simply, how I can achieve? Now my task is to achieve and find the value of x mod 10. Again, make sure that x right now is nCr, but again, I'm just saying x can be any value, just find the mod with 10. And again, this can be a very large value, let's say. So now I just give me 1 sec and let's see what is happening. Okay, I'll come in a sec. I'll come in a sec. Okay, sorry for that thing. I got my lens just now, camera lens. Okay, let's continue. So we were trying to find, I have to find x mod 10, and x can be a very big thing. So obviously I can only do with the prime numbers, and that's the thing. And 10 is not a prime number. So how to go about that? Obviously, let's break it down. I will break 10 down to prime numbers, which is 2 and 5. Now, how this will help me? Let's see. If by any chance, obviously, now this is prime, which means that nCr mod 2 I can find easily, right? nCr mod 5 I can find easily. If you don't know how to find it, obviously please go and watch the above video. Now you should be easily able to find this value easily. Now if you are able to find it, which means x mod 2 you were able to find the value v2. Okay, x mod 5 you were able to find the value v5. Imagine that you knew x again, not like, please don't imagine, you knew x for sure, which is nCr. You mod like 2 you knew, you will be able to find v2. That's so this is this is x obviously nCr, 5 v5 you will be able to find by simple nCr mod p formula. X mod 10 Now your task is that okay, you were able to find these things now, but your main target was to find with mod 10 and not with mod 5 and 2. So how will I achieve that? How will I achieve that? Again, although you can try to think in terms of Chinese remainder theorem, but again, that's a bit of overkill. I have written that here as well. Just go simply in terms of that obviously anything mod 10, the values will be in the range of 0 to 9. That's it, right? The answer, obviously this thing will be in the range of 0 to 9. So I can imagine that x itself would have been in the range of 0 to 9. Again, obviously x is very large. So, but just to think of that how the answer is written here, imagine that if this thing is 9, so obviously mod 10 will no more make sense. Will no more be required. I can just directly copy 9 here. So now I said that because, okay, the back is not working somehow. Yeah, so now I mentioned, okay, my search is happening. Yeah, so now I mentioned that if I just go back, yeah, a bit, yes. So now I said that, yeah, why it is, okay, forget about this. Yeah, now, yeah, it is, okay. Now I said that this value I know will be from 0 to 9, but I have to find it. Which one? I have to find it, which one? So I said, okay, just do one thing. Try for this specific x. Try for this specific x and just imagine this as all the values from 0 to 9. But obviously it should satisfy this condition as well, which I have already found with the correct value of x. So what I will do now, I will try for 0, 1, 2, up to so on and so forth up till 9. And making sure that 0 mod 2 should give v2, 0 mod 5 should give v5. Again, if this gives, if v2 and v5 are correct, obviously if v2 and v5 are 0 in this case, I will say okay, 0 is my correct answer. Right, and then if v1 is 1 mod 2 will give me 1 and 1 mod 5 will give me 1. So if v2 and v5 are 1, okay, then 1 is my correct answer for x mod 10. If 0 and 2 are my values, obviously if let's say v2 is 0, v5 is 2, in that case I will simply say that okay, great, my x mod 10 is nothing but a 2. So this is how I can simply go about and easily tell with the help of these two results that what is my x mod 10 value. Now if you want to go deep and just want to understand, you can go and understand Chinese Remainder Theorem. It simply says that if I have some value x mod 2, and I'm given some value, let's say here, which is 3. No, 3 is not possible, let's say 1. and then I have another value which is x mod 5, which is another value, and then x mod 7, another value. So with that, you will be easily able to figure out corresponding value of x which can give or satisfy all of these conditions. So imagine here these all are given, and thus you will be easily able to figure out the x in this case. This is nothing but a Chinese remainder theorem. Technically, you can apply the same thing here, and this logic is derived technically from this only. But again, as I mentioned, as I told you, you don't have to specifically go about it. As I mentioned, just go and try for all the values from this 0 to 9, and it should satisfy these two conditions, because LCM of 2 and 5 is 10. Now, considering you know that, your now problem becomes that simply go and find x mod 5 and x mod 2, which is go and find nCr mod 5 and nCr mod 2. Now again, you don't need any complex Lucas or anything of that sort. You can easily find this out with the existing knowledge of nCr, which I told you, right, we have already seen previously in this video. You will be able to find with this knowledge, but as an extra add-on, we realize that technically whatever we have found out for nCr values, it is with mod p, and their p is very large prime number, 199 plus 7, 199 plus 11, like that. But here the mod is value very small, right? Now, can I leverage that? Again, the answer will not change. You will still, with the existing knowledge of nCr mod p, you will be still able to find the answer. Now, whatever I'm telling is nothing but extra. Lucas theorem is nothing but extra in this case, not necessarily needed, but obviously will help you improvise the space. Let's see how. So obviously we realize that if you want to find nCr with a very large value of n and r, right? Because n and r can be 1e5, less than 1e5, because my length of string can be up till 1e5. So in that case, obviously I will have to find the factorial, right? Factorial for all the numbers from 1 to 1e5, which I have done earlier also in the existing problems. Now, can we optimize this? Yes, maybe we can. How? Let's see Lucas theorem. Lucas theorem is simply it simply help us to find nCr mod p. But obviously in this case, we should make sure that, okay, p can be anything of that sort, but whenever you have a different p, or when p is small, right, in that case it is much more beneficial to use Lucas. Let's see what Lucas says. Lucas says that obviously there's a pattern when we do a modulo, and if you remember, nCr is entirely nothing but Pascal's triangle based, right? In the entire Pascal's triangle, I can represent every value as nCr. That is the reason Lucas is built on top of Pascal's triangle itself, and again primarily needed for nCr, to compute nCr. Now Lucas says that if I do a mod with any p prime number, now again, for example, p, let's say, is 2, then obviously you will see that a pattern forms like this. You see a pattern forming, and this is the pattern being formed. Same way, you will see the pattern being formed keeps on increasing, right? Like it keeps on becoming a pattern. Now, what I mean by that and how I can leverage that pattern, let's see. Firstly, I'm hoping that you know very basic Pascal's approach, or Pascal's trick, as I mentioned previously also. If this is nCr, if this is nck, which is 4c2, then I can easily write it down, nck, I can write it down n minus 1 ck minus 1 plus n minus 1 ck. This is also can be derived from Pascal's, because this is n minus 1 ck minus 1, this is n minus 1 ck. So adding of these two gives me nothing but this thing, which you obviously know. So I just represented the same Pascal's formula with the help of its corresponding nCr. Now, the theorem of Lucas says that please go and find the base prime number. What is that base of prime number? The base of any number says, if I have number 1038, in base 10, I can show that number as 1038. How? Obviously, 1 into 1e3, 0 into 1e2, 3 into 1e1, and 8 into 1e0. With that, I have represented this number as a base of 10. But obviously, this works with prime numbers. So if I have to say for another prime number will be 5 or 2 or any other prime number. How I can represent this as in a form of base? So I will represent 1038 as a base of 5. How to do that? I hope you must have done that very basic problem in arrays itself. We have discussed this problem of base conversion, right? I'm guessing you must have done array easy at least. So with that, we know that how to do that. Again, I'll just give a quick glimpse. If I have 1038, I have want to convert it to base 5. I will divide it by 10. Sorry, I will divide it by 5. Whatever is my remainder, okay, 3 into 5 raised power 0. Same way, whatever the question, just get it down here, divide by 5 again. Whatever is the remainder, 2 into 5 raised power 1. As you can see, 2 into 5 raised power 1. Same way, whatever is the question, get it down, divide by 5. Remainder, 1 into 5 raised power 2. 1 into 5 raised power 2. Same way, get 8 down, divide by 5, I get a 3. So 3 into 5 raised power 3. So again, 3 into 5 raised power 3. And lastly, get 1 down, 5 divided by 0, remainder 1, 1 into 5 raised power 4. 1 into 5 raised power 4. This is how you can simply convert to any base whatsoever. I'll convert to base 5 and base 2, but obviously you can convert to any base. But Lucas says that if you have n and k, obviously your main task was finding nCk mod p. This was your task to find. Now, Lucas mentioned that, okay, n and k are two different things. Okay, for n, with a base of p, find what all things can be there. For example, he will say that for n as 1038 with a base of 5, find me the actual values, which is 1, 3, 1, 2, 3. Same way, do the same thing for k. Now, when you have done this thing, so nCk mod p will be nothing but individual values nck. So it will be, again, let's say if it is nr or kr, so it is nr ckr. And same way, if it is, let's say, nr minus 1 kr minus 1, so it will be nr minus 1 ckr minus 1, and so on and so forth up till n0 ck0. And again, obviously, this is the multiplication. So in the very last, do a mod with p. So if I ask you for this 1038 c 696, although you can find it by saying 1038 factorial divided by 696 factorial and 1038 minus 696 factorial, and then doing a mod with 13, that's all absolutely fine and will be working. But obviously, this will take a space. And when I say space, obviously you have to find factorial. So you have to pre-compute factorial, and that takes a space. So how to get rid of that? We will use our Lucas theorem. Lucas theorem says that for this n, find me for the base 13 all the values. It will be 6, 1 and 11. Same way, for 696, find me all the values, which is 4, 1 and 7. Again, with the base of 13 itself, which is a prime number. With that, now I will do 6c4, 1c1, 11c7. 6c4, 1c1, 11c7. But making sure that it's a multiplication, so do a mod with 13. Ultimately, I get a value of 10. So, with that, because I am doing a base 13 conversion, all the values will be less than 13. Because of that, nc, again, let's say it is nic ki. So ni and ki will also be less than 13, which means that I will actually be dealing at max up till 13 factorial. Thus, I don't have to compute anything higher than 13 factorial. So whenever I'm computing n factorial upon r factorial into n minus r factorial, I have to compute only up till 13 factorial. Both factorial and its inverse factorial needs to be computed only up till 13. And that's how I can save my space. So Lucas helps us to save the space, which, okay, it's good. That's it. That's the only thing. Again, the only reason why Lucas is good for this is for using space. That's it. Elsewise, you could have simply applied your simple approach as well. Now, lastly, I mentioned that when and why to use Lucas. Obviously, when your prime number is less and small, which means that obviously in this case you will see that you have to find nck mod 2 and nck mod 5. But if for example, again, obviously in this case it is much beneficial that like obviously if you find nck mod 2, nck mod 5, which means that you have to pre-compute n factorial mod 2 and you have to also pre-compute n factorial mod 5. Again, you will understand all these things only and only when if you would have watched these, again, at least one of these videos, that how n factorial is computed or how ncr is computed. So to again, just to get rid of this thing, because obviously you have to pre-compute the factorial values and all that stuff. You can use that. And again, as I mentioned, that the number of values should be less, because here again I am even if it is not less, that's also okay, but small is a good thing, because if it's a large, then why to even use of it? Because it will not help me that much. But again, this is ultimately what your Lucas can help you to achieve. Now, ultimately, if I give a quick recap, what we did, let's give a quick recap and then we'll go on to the code. So, firstly, we figured out the pattern from this entire tree and figured out that the actual values are the string values and their corresponding coefficients are nothing but derived from the Pascal's triangle. With that, because I know for a specific row I can find the entire coefficients of the Pascal's triangle, so I know if I have 4 elements, I will have 3 as a row number. I will compute its coefficients easily. But obviously, I will have to do a mod with a 10 and I don't know how to do it. So I went ahead and divided it into 2 and 5. Now, because I know a rough idea of Chinese Remainder Theorem, even if not, I will see the LCM of 5 and 2 will give me a value of 10, and thus I can say that for a value of 10, if I am able to try for all the possible values of 0 to 9, I can put these values here and try to see which one achieves the same result of V2 and V5. If yes, I will be good to go. And when I say good to go, which means okay, I just now have my task to compute V2 and V5. To do that, I went ahead and tried to find nCr mod 5, or I should say X mod 5. I can apply a simple nCr here as well, but I thought, okay, because 5 is very small and n and r are very large, so in that case, let's try to use Lucas theorem. Lucas theorem mentioned that make sure that you find the base values for a number in 5, and because it's a base of 5, so all these numbers will be less than 5. In that case, my NCR will only be computing NCR value where N and R are less than 5. In that case, I will save upon memory, because I don't have to compute my entire factorial values up till 1e5. And that's how we can find NCR mod 2 and also NCR mod 5. And again, when we have these two values, which is V2 and V5, I can try for all the values from 0 to 9 and see which value fits these two equations. And that value will be nothing but my x mod 10 value. And if I have a x mod 10 value, I will just simply keep on placing here. And that's how I can get my answer. Now, please make sure that you like and achieve the like target of 100 likes. Let's see the code. Now the code says that obviously, as you remembered, I have to go up till what point? As I mentioned, I have to go up till n minus 2, right? Up till n minus 2. And how and what I will do that and what I will do there? I will have to find this thing, which is the sum. But again, this sum is built up of digits and their corresponding coefficients. Coefficient I will find by using my NCR. So I'll do NCR mod 10. So this is nothing but, if I just go down, where it is gone? Yeah. So if I just go down, it is nothing but NCR mod 10 I am finding, and this is my digit. And this is up till my digit n minus 2. So if I go up, I will be finding the coefficient and this digit d1. So I will say d1 into coefficient. And again, I have to take the summation. So I'm just taking a simple summation and doing a mod 10 here. Again, mod 10 here will not impact because it's a simple a plus b mod 10. But here it will impact because here it is NCI mod 10. Here in this case, I have to apply that Chinese Remainder Theorem concept technically. So I will simply go down, and again, please don't be confused, right? With the normal Chinese Remainder Theorem, I simply explained you how you can infer the actual thing, what you needed from that specific thing. Cool. Now I will come on here and I have to find again, just so as to complete this piece of code, I will do the same thing, with the d1, and I'll do the same thing with d2, and I have to make sure that both are same. Now coming on that, how I will find the nck mod 10. As I told you, I will have to find firstly nck mod 2 value, which is nothing but x mod 2. So this is nothing but its value is mod 2 value. Same way I will find x mod 5, right? Again, this x is nothing but nck, right? And that value is mod 5 value. Now I know mod 2 value, now I know mod 5 value, I know 2, I know 5. Now I have to find, okay, x mod 10 should be what? Now I know the options can be from 0 to 9. So I will try all the values or all the candidates from 0 to 9, and I will see that which one. 0, the candidate mod 2 equal to mod value, and the candidate mod 5 equal to the mod value. If any candidates satisfy both of them, obviously that's a good candidate for me, which will satisfy this as well. And ultimately I can return that specific candidate. If not, then 0, but obviously I will be good with the candidate itself here. Now, if I come on, I can find any nck. Now my task is to find nck mod 2. I can find this easily without knowing Lucas, but obviously we can use leverage, or we can leverage Lucas. Lucas will say just do nothing, find the base 2 values for n and k, and then do their individual c, or I should say do their individual nck. So I will keep on going up till my n and k are there, find the n digit and k digit, which is nothing but, remainder. As I told you in the dry run itself, I find the remainder, and then obviously if my k is higher than n, if for nck, if k is higher than n, obviously it results in a 0. That's a very normal nCr concept. Now, elsewise, I can apply now my Lucas theorem. Lucas theorem says that multiply, keep on multiplying individual base values, base results. Keep on multiplying them, which means I will find individual base results and doing their nCr and then multiplying them. For that, again, I need to know the actual nCr. So this is actual nCr. This is Lucas nCr. Lucas nCr is trying to find the base values and then doing their nck. But still, nck is still required. If I go back, and go down, way down, yeah. Technically, I am simplifying this 1038C 696, but still 6C4, 1C1, 11C7. So nck is still required. So in that case, just to go, I will still have to do a nck, which means I still have to go and find n factorial upon r factorial to n minus r factorial. The only catch here is because I'm doing a mod with a prime number which is 5 and 2, thus it will be pretty easy. Now, if I will do that, okay, I will get that result and I will pass it here. And again, making sure that repeating that process until your n and k are not empty. Again, as you saw in dry run. Now, if I check for nck mod 2, the only possible result can be a 0 or a 1. Can be a 0 or a 1. Obviously, if my k is more than n, it will always be a 0. Elsewise, it will always be a 1. And you can also see that do anything whatsoever. Do anything. Let's say if you do nc0 or nc like anything, do nc1, nc2, anything you do, and again here in this case you will see that the n itself will also be less than 2. So here if I am doing this thing n and k, so both n and k, both n digit will be either a 0 or a 1, k digit will also be 0 or a 1, 0 or a 1. In that case, 0C0, 0C1, 1C0, 1C1. It is a 1, it is a 1, it is a 0, it is a 0C0 is, again, this is a 0, and because this is not possible technically. And again, this I can say is a 1, yeah, I can say it's a 1. So you know that obviously answer will be 1 in any which case. Now, the same thing I will do for nck Luca modulo 5. Again, the exact same concept, find the remainder and make sure to pass that to actual nck with n and k value. Now, this thing again, the remaining code is exactly same as nck Luca mod 2. Now, why they have two separate piece of code? That is something, yes, it is not required because you can actually pass this to as a function, but yeah, still it's okay. Now, for actual nck mod 5, now I apply the actual concept of nck. What says nck mod 5 will say nothing but n factorial upon r factorial into n minus r factorial, do a mod with 5, which means that n factorial mod 5 and doing the inverse of this denominator. So this is nothing but r factorial into n minus r factorial, but it's an inverse, right? Again, I'm sure you must be knowing inverse and how to find NCR. If not, then video again. But it will find r factorial into n minus r factorial, but the inverse of it, right? The inverse of it, and that is inverse we can find by multiple ways. You can involve modular explanation as well in this case, but because 5 is a very small number, as I mentioned for the prime, thus I will find the numerator, I will find the denominator, then I have to find the denominator inverse because I have to multiply with the denominator inverse. Now, again, if you don't know, to find the denominator inverse, you can apply inverse here. But again, to apply inverse, you also need to write the binary explanation code. So it will involve two code snippets as well. So how to get rid of it? Just make sure, what is this? What is this? You are trying to find what? You are trying to find the inverse. So inverse is nothing but, so if I say you're trying to find the inverse. Inverse is 1 upon x. So technically, for this denominator, you are trying to find its inverse, or trying to say that, okay, this mod p should be same. So it is nothing but x inverse. C is nothing but x inverse. So to find your C, I can multiply my x here, and I will say that x, which is nothing but my denominator, right? This denominator, and the candidate, which is C, mod with p should be 1. Any such candidate is nothing but my denominator inverse. So C will be my denominator inverse, which is 1 by x mod p. So this is how I can get, by simply trading on 5 values, I can get my denominator inverse. Again, as I told you, you can use the modulo inverse here as well, but for that you have to write the binomial explanation as well, which is kind of overkill. Ultimately, when I have numerator, when I have denominator inverse, I will multiply them, and again, making sure to do a mod with at every step, I will get my NCR mod 5. And that's how we can simply get the corresponding NCR value. Cool, I hope you guys got it. Again, the video got a bit long, but please make sure that these videos take a lot of effort, where there are a lot of things which are clubbed in, and again, we try to bring it to you so that you like it, appreciate it, share it, and give your love. Bye bye, take care. I'll not make the video a bit long.